Yeah, thanks for joining today. My name is Nikhil. I'm a lead applied scientist at Wayve, focusing mainly on offline evaluation using tools like GhostGym to sort of validate our driving system. And today I'm going to talk about how we use neural simulators at Wayve and also how we're looking at measuring progress in this field. Cool. So just a quick overview of the agenda today. I'm going to talk briefly about how we are using neural simulators at Wayve and why they're needed in the AV 2.0 field. And then I want to talk a little bit about how we're thinking about benchmarking environment creation for neural simulators, as well as talk a little bit about the new data set that we're releasing to help inspire progress in the field, and then some concluding remarks. Cool. So why do we need a closed loop simulator for it, right? So I'm sure if you guys have been to Wayve presentations before, you've seen this slide many a times. But this slide highlights the differences between the classical AV 1.0 approach and AV 2.0. So if we look at the AV 1.0 approach, it's sort of a very modular stack that where we go from have a pipelined approach of sensors in perception, planning, and control. As opposed to this, if we look at AV 2.0, we have our sensor input coming in, and we have one neural network that is optimized to do both perception and planning in parallel. So this is a new way of thinking about driving, and instead of trying to solve it with robotics, we try to develop a system that mirrors the way a human thinks about driving. So given this, what are the implications for how we actually design our simulators to accommodate this? So if we look at AV 1.0, and if we look at sort of validating the two big components in the stack, being perception and planning, we can start with perception on the left. So in a perception system, there's no sort of decision-making component in the system. So we can actually utilize open loop data to validate the accuracy of our perception systems. Since there's no decision-making component, there's no domain gap between offline and online predictions. And so this is a very effective way to benchmark perception systems. And on the right, if we look at the sort of how we validate planning systems in AV 1.0, since the planning stack operates on top of the outputs of the perception system, we can actually do this closed loop. We can do this closed loop simulation directly in the perception space. So what this means is the closed loop simulation engine can actually be it's a much simpler task, given you don't have to actually synthesize novel views directly in sensor space. Whereas if we look at AV 2.0, and given we're doing perception and planning in parallel, we need to actually, to develop a closed loop simulator, we actually have to synthesize novel views directly in sensor space. And on top of this, not only do we have to sort of render things directly in sensor space, but they actually have to be very photorealistic, and the domain gap to the real world has to be low. Yeah. So if we then look at how we actually would use or how we think about development of AV 2.0, one of the big desirable properties is when we observe a disengagement in the real world, we don't want to make the same mistake twice. So here's an example where we have a real world disengagement, where we have the model, where we have an empty zebra crossing in central London. And we can see that the driving model and control sort of unnecessarily slowed down at this empty crossing, which is not desirable, given you can sort of continue at your current speed. So given this disengagement, now we really want to make sure that we never have the same disengagement again. And we want to be able to sort of prove this with our offline systems. So if we start to think about, how we can actually go about doing this, what are the options we actually have here? So the first option is open loop verification. Here, we're just using the logged sensor data from the real world and running it through the next iteration of our driving model to measure how it would perform in these log states. So the really good thing about open loop verification is the domain gap is 0, given you're actually using the real images to run through your new model. So it's very, the predictions are actually very indicative of what would be the prediction at these states in the real world. One of the difficult things with open loop verification is because it's open loop, you can't actually see the outcomes of the decisions that the model made. So what this means is you only really get directional signal about how the model is improving offline. So if we look, for example, at this video on the left, we have a new model being tested in these log states, and the waypoints are in orange, whereas the original model is in blue. And we can see that the new model is predicting a much more consistent speed going through the zebra crossing. But still, given this, how can we actually know if this sort of prediction was sufficient to avoid a disengagement in the scenario? It's very difficult to do, even as humans, because we don't actually know what the next prediction at the new state would have been. But with that being said, open loop verification is very cheap to run, and we can scale this to thousands, if not millions of scenarios. And at this scale, the directional improvement can start to really provide valuable insights. When you have millions of these tests running and you're getting directional signal on each one of these tests, you can actually start to make, you can actually start to provide scores for the new model and control. So after open loop verification, another option we have is sort of creating a hand-designed digital twin, similar to the engine like Carla. The main advantage of a system like this over open loop is that it's closed loop. So you can actually see the outcomes of the decisions that the model made. But even with expert technical artists, generally the domain gap remains quite high to the real world. So it's very difficult to make the jump and say, if we have a hand-designed digital twin of the scenario, it's very difficult to make the leap and say that this disengagement wouldn't have occurred in the real world as well. And once we actually move to the resimulation domain, this burden on technical artists actually increases even more, because they not only have to sort of create realistic looking assets, but they actually have to match the distribution or the assets we saw in a particular scenario. And so scaling these kinds of systems to every disengagement you see and want to create unit tests with is really difficult, since the main bottleneck here is the human effort to create the environments. And yeah, now if you look at the third option is using a neural simulator, which we all love. So if we look at the properties of a neural simulator, it's also closed loop. So you can actually allow the model to change the state transition away from the logged images. So you can actually start to move away from just observing decisions and move towards looking at what outcomes would have been. A neural simulator uses a data-driven environment creation, which, because of how the optimization of the environment is done, it is directly trying to match the real-world distribution of the scenario we see. So what this means is there's no requirement for a technical artist or a human in the loop. We can pass video data in and get 3D or 4D simulation out. And this makes it super suitable for the resimulation use case, where we actually want to take the scenario we saw on the road, replay it offline, and allow the new model to actually control the sort of actually have control of the state transition. So now if we look back at the original example we started off with, so again, we see on the left that we have this real world disengagement of the model slowing down. And on the right, we can see the same model we saw before with the orange waypoints. We now see it being tested in Ghostum, where we can see the speed stays consistent through the zebra crossing and doesn't have this dipping behavior. So we can actually now see that the outcome of these predictions compounded, and we can make more, we can with more confidence make statements and say that the new model wouldn't have also had this disengagement. And for us, this is huge because being able to do this offline, I mean, when you go in the real world, you'll never see the same situation twice. And so you need simulation to actually make comparisons between two models on the same scenario. And we're seeing a shift in this direction throughout the industry, not just at Wayve, where Unisim from Wayve, NeurAD, just a few examples, but we're starting to see the whole industry move in this direction of utilizing data-driven techniques for simulation. Yeah, and now, I mean, one of the big aspects of a neural simulator is the environment that's used to actually represent the world in the simulation. Earlier this week, we announced Prism 1, one of our works to reconstruct 4D scenes directly from video data. And it's used in Ghostgym, our neural simulator, to actually synthesize the environment such that a new driving model can be driven offline. So today I want to look a little bit deeper into the environment generation and how we can start to measure our progress towards creating better environments. So yeah, how do we actually measure the quality of these reconstructions? So first and foremost, we gotta keep things simple. We gotta have image-based metrics. So these are things like photometric reconstruction quality metrics. Pick your favorite metric, PSNR, LPIPS, SSIM. They're all super useful in being able to actually benchmark and test the quality of how our environment, how our simulated environment matches the real distribution. In addition to this, we can use geometric cues such as depth, surface normals, etc., to actually make sure the environment is not only photometrically accurate, but also geometrically represents geometrically represents the true scene that we see. Next, we have downstream metrics, right? So one of the use cases we have is resimulation. And so to go beyond just image-based metrics, we actually want to measure how low the domain gap is in the use case that it's going to be used for. So one of the big metrics we use to actually benchmark our environment creation is what we like to call reproducibility. It's pretty intuitive in that what we are trying to measure here is we take the same driving model that drove in a scenario on the road, we run it offline, and we measure how different the observed trajectory is offline to online. And this gives us a measure of the perceived domain gap by the driving model between the real world and the simulation. While this does benchmark the environment creation itself, it also provides a metric on how well we're able to actually resimulate the robot, things like the latency, the latency, the vehicle dynamics model. So it's not isolating just the environment itself, but it's sort of a better measure of the full simulation system as a whole. But nonetheless, super valuable to actually measure how the fidelity of the simulation. And another metric is normal view synthesis. So this is sort of in some sense, a privileged metric in a lot of ways, because you want to somehow measure what the image quality is when you're away from the sort of training views you use to train the environment model. So especially in domains like driving, this starts to become very relevant because most of the captures have these linear types of motion. Out there, at least for autonomous driving, where we're able to effectively benchmark how well we're doing in these off-axis poses. And yeah, we need to have this such that we can make progress in the field. So yeah, I want to take this opportunity to then sort of go over, why we need this and what's out there today, and how we at Wayve are trying to help make progress on this and solve this problem. So if you look at benchmarks in machine learning over time, we see a pretty clear trend here that once a benchmark is sort of established, we get closer to human level performance, eventually surpass human level performance. And then we find that, these data sets are no longer effective ways for us to actually continue to make progress in the field. So we can see this on the left. We started with image classification. We crossed human level performance. There was a need for harder tasks to measure how well we're doing. So we moved to reading, language, and then eventually we go to competition math. And once these benchmarks are established, the community is very good about optimizing for these metrics and eventually surpassing human level performance. So if we look at image classification, the classic example of how this started is ImageNet, and ImageNet really arguably started or was the base data set on top of which the deep learning revolution started. We had lots of innovations here, like AlexNet, Dropout, ResNets, many, many more. And it was really crucial in the early days of computer vision for us to measure progress in the field. But eventually, we got very good at ImageNet, and there was a need for something better. So what do? We sort of moved to harder perception tasks. We moved from global image level classification to tasks like semantic segmentation, which required us to not only give a class for a full image, but a per pixel class ID for images. And we also moved to tasks such as visual question answering, where it required a higher level of reasoning, where, for example, in this pizza, you have to actually reason about what's in the image and the contents of it to be able to effectively answer these questions. So once we moved to these tasks, we were getting closer and closer to actual real world use cases. And these were very effective data sets and metrics for us to actually continue to measure progress. And I mean, now the computer vision benchmarks are much more aligned with how we actually are going to use them in the real world. So if we go back to sort of novel view synthesis and we look at how the same evolution happened here, I'm sure if you've trained a nerve or a Gaussian splat in your life, you've seen this tractor. It was a perfect first example of how we can measure and actually prove that this problem is solvable in a small toy domain. And while it was great initially for measuring progress, you'd argue that, I mean, no longer sort of the benchmark that people are using to benchmark new work. Then we move away from these synthetic data examples to real world captures, still very controlled, object-centric scenes, but moving in this direction of getting to harder and harder tasks such that we can continue to push the boundaries of what's possible. After that, we started to see even these examples. Most methods out there today in the NVS domain are pretty good at those problems. So we wanted to make the problem even harder and start making things move. So here we see some example of the early days of dynamic nerve data sets, where people sort of took these synthetic objects and started making some movements in them and try to see if we can actually get an algorithm that faithfully reconstructs these 4D scenes. And this is a work that I really like from the folks at Berkeley, where they talk a little bit about how we can actually quantify how causal and dynamic a data set is. So if you look at the data sets, or most of the data sets I showed you in the last slide, they fall in this right-hand side category, where we either have a very controlled setup where we have multiple cameras looking at the scene from different viewpoints, or we have teleporting cameras where we just have like random instantiations of various cameras in the scene. Yeah, but so these captures are actually, they don't reflect how data captures are going to happen in the real world. In the real world, you're going to have an iPhone, you're going to move through a room, or you're going to have a vehicle, a robot that's basically moving through an environment. And they're going to be capturing these videos in a causal manner through the scene, rather than having a teleporting camera or having multiple studio-like setups. So we continue to see, okay, now we've seen methods that are able to solve this problem in this controlled setup, but now we actually want to move towards this left-hand side, where we have models that actually work with data distributions we'll see in the real world. So one of the sort of big sources of causal data captures in the real world is autonomous driving data sets. So, I mean, great works, I mean, that we've seen, I mean, Kitty 360, New Scenes, Waymo Open data set. They're all great data sets for various purposes. And we see that the novel view synthesis community has sort of gone to these data sets to sort of further challenge themselves with data that reflects actual real captures and getting them to work in these environments. We look at these autonomous driving data sets, they're causal, they're dynamic, they're outdoor, So they sort of check all the boxes in terms of the difficulties of getting these methods to work in the real world. And so this is how the community is really starting to challenge themselves. But if we look at sort of how these data sets have been designed, they're mostly designed specifically for the use cases of perception and planning. So what this means is the sort of setup of the data set, the distribution of scenes that are present are all sort of optimized for these tasks of perception and planning, and are not necessarily choosing things that are hard in the novel view synthesis domain. We also see, I mean, from the previous slide, that these rig setups are all, they're 360-degree rig setups, but the amount of overlap between the cameras is quite minimal. In the image on the bottom, you can see the overlap between the cameras in the Waymo open dataset. And this makes it impossible to actually have this metric of off-axis reconstruction quality, because you don't have any redundancy in views where you can drop out a particular camera view and use that for the purpose of off-axis metrics. And each of these data sets sort of have their own format and sort of storage and way to sort of access the data. And this makes a lot of sense given these are more general purpose data sets and have a lot of different challenges. But when you actually start to try to utilize these for NVS domains, it becomes quite tricky to integrate these data sets into existing frameworks. So because of this, we saw the need for a new data set that's particularly tailored for the challenge of novel view synthesis, that we call Wayve Scenes 101. So Wayve Scenes 101 is an autonomous driving data set, specifically for this task of novel view synthesis, and I'll talk a little bit about the properties that make this data set unique. So firstly, the camera setup. So we really tried to curate this camera setup such that it would be the most useful setup for this task. So as you can see in this image, our rig consists of 5 cameras, 4 of them wide-angle fisheye cameras, the blue frustrums you can see in the image on the left. And in the middle of we have this, what we're trying to get to as an evaluation camera that you can use to actually benchmark how well your reconstructions stay off the sort of training axes. So if we actually look at what this looks like, if you look at the RGB views from a snippet of this data set, you can see that this image in red is the sort of front-forward camera that's we use for evaluation. And you can see on the 2 adjacent cameras on the left and right of the vehicle that can be used for training. So what this means is you have enough overlap with the training views that you can actually effectively use this as a metric for off-axis reconstructions, but also makes the problem tractable where you're not using like a camera that has no overlap and makes the task. It's at the right balance between difficulty and usability. So if we actually start to look at the sort of how the diversity of the data set and how we've tried to curate it such that it's suitable for this challenge of novel view synthesis, we collected data across 2 countries, so the US and UK, day and night. We've also tried to put a special emphasis on things that like changing illumination in the scene. So you'll see a lot of scenes that have things like changing traffic lights, brake lights coming on and off, blinking indicators. And this is really done to reflect the challenge of being able to faithfully reconstruct this in simulation. Dynamic objects, so you'll see vehicles, but also pedestrians, cyclists, and deformable objects that are generally very difficult to make work with scene graph type approaches where you sort of try to compositionally arrange the scene. Also things like exposure changes and variable distances traveled in each segment makes the data set a good sort of way for the community to measure what we're currently good at and what currently needs improvement. So just some visuals to give you a feel for what's actually in there. So here we can sort of see, we also want to benchmark static scenes. So here are some examples of static scenes you'll see in the data set across residential and highway, both posing their own unique challenges. One, you travel much further, and one, there's just a much more detail into vegetation and houses on the roads. Dynamic vehicles. So again, you can see two very different scenes here. One in central London with very sort of complex behaviors of the vehicles that we're interacting with at lower speeds. And on the bottom, you'll see, more of a American highway type scene where things are moving really fast, but maybe a less complex motion profile. In addition to this, changing camera exposure, examples like going through tunnels, lens glare. These are all challenges that we face in the real world, and so we wanted to sort of reflect these challenges and pick scenes that specifically highlight maybe more extreme cases of this in the data set. Deformable objects, or as we like to call humans. These are some examples of scenes where there's a lot of humans in the scene, cyclists, and really sort of can highlight maybe strengths and weaknesses of a particular approach. Changing illumination. Talked about changing traffic lights. Here we can see two scenes with temporary traffic lights in the UK, sort of more classical American traffic lights in the below. And we've selected segments particularly where these state transitions happen. And so you can actually start to benchmark if you're able to model these state transitions effectively. This is another one. A tough one is night scenes and how we can handle those when we do normal view synthesis. You can see some examples of this. Lots of challenges here. Just lower light in general makes the problem harder, but also you start to see a lot more sources of active lighting in the scene, such as the ego vehicle headlights, but also things like other vehicles, lampposts in the scene. And so we think this can also be effective to benchmark works that are specifically targeted for things like low light or night settings. So that's a little bit about the diversity of the data set. We also want to talk a little bit about, just structure for motion format. We know in novel view synthesis, NeRF Gaussian splatting, call map is king. Sort of most of the academic community utilizes call map as a source of posed information as well as 3D point information. So we've deliberately chosen to provide all of our sort of posed and calibration and 3D environment information in this call map format, such that it can as easily be integrated into existing NVS code bases and projects with minimal effort. Here you can see an example, NeRF Studio, a very popular framework for training Gaussian splats and NeRFs. You can see sort of the ease and how easy it is to actually start training a model on a particular scene in the data set. This is all possible in about 2 lines of code where you just utilize some of their inbuilt functionality to actually convert the call map information into a format that they have, and then you start training. So this, we believe, will really reduce the barrier to be able to actually get more sort of people from the NVS community involved in actually benchmarking in autonomous domains and actually starting to test how robust their algorithms are. So I mean, now if we look at this table again, so we've released 101 scenes to begin with. We are looking to add more scenes in the future, but we wanted to start with something small, such that we can iterate and get feedback from the community on what's valuable within these scenes. We do now have a held out camera for evaluation, so we can start to actually get quantitative metrics on top of the qualitative evaluations we do for novel view synthesis. And it's specifically built for this novel view synthesis use case. And so it makes integration with existing libraries much easier. Cool. So just to wrap up, some final remarks, some key takeaways. So we've spoken a little bit about how launch simulators are key to accelerate the development of autonomous vehicles, and why they're sort of needed to actually do scalable closed loop evaluation for development. We've talked a little bit about how benchmarking of current novel view synthesis methods is primarily image-based metrics and application-based metrics, but are lacking novel view synthesis metrics, where most of the sort of evaluations are qualitative. And lastly, we introduced a new data set that we've released to tackle these challenges with benchmarking and novel view synthesis. And we hope to inspire more progress in the field with this, on top of sort of what we're doing at Wayve to accelerate this field. Yeah, and this data set specifically curated for this task. And that's it for me today. Thank you very much. If this kind of work sounds interesting to you, we are hiring, so come get in touch with us at our booth. The team will be there tomorrow, and love to catch up with you guys.
I think we have time for one question. Go fastest hand in the room.
So if you could go back to one slide, which was on novel synthesis slide when you introduced that, there was a scene where you had a car approaching a traffic intersection.
Yeah.
Came from the right to green.
Is it this one?
No, I think it was one of the earlier slides that you had.
Okay.
Yeah, well, like really at the beginning of the presentation. Yeah, on the right hand side. So one of the things that I noticed was there's a small artifact that appears right above one of the lights in the right hand image. And my question is, do you have pixel level control over the scenes that are reconstructed? And my motivation for that question is, how resilient are the metrics that you're using to ensure that there'll be a downstream accidental artifact that's generated during the reconstruction process?
I see. So if I understand the question correctly, so you're asking how much controllability we have over the over
the reconstruction to correct if there's artifacts, if there's ways to measure accidental artifacts that appear in that process. That way you don't include that in the training or the evaluation process later on.
Yeah, it's a good question. So just to repeat it for online folks, the question is how we can detect or detect artifacts that occur in the reconstruction, such that we can maybe exclude that data for use downstream use cases. I mean, one of the like we spoke about, generally measuring the quality, we sort of use a multi-pronged approach here, where we try to measure, I mean, if the artifacts in the sense of downstream reproducibility use cases. So that's one measure of how we can actually measure this domain gap. But I mean, the sort of challenge is really when you're getting off axis, right? So this is where we find that having held out cameras that are not along the views is much more reliable in actually exposing these bad geometric reconstructions or artifacts in the reconstructions. And that's really why we've tried to sort of go down this way of evaluating. Cool, thanks.